The book talks about them too, clearly, but we've diverged a lot from some of the book stuff because there's easier ways to do it since he's published it. So, all right. So getting into how do I run these things. So if you have the data in wide format, go ahead and screen it that way. Stacking and unstacking the data is a little hard sometimes. It won't hurt you to screen it in long format. You will just have to think about percent missing differently. The analysis, though, has to be in long format, right? And you must have a participant number. So we've done every analysis so far in long format, but participant numbers didn't matter. Now it's super important because that's how we're going to control for the fact that people are repeated. And if you have missing data, so let's say you have participant in items 1, 2, 3, and you don't have 4, it's got to know that that participant only has 3 time points. Okay, so we've got to have a participant number, so we're going to talk about how to add those today. And then we are going to use the ezANOVA function in the package ez. And I say this is a traditional style because this is running it as a repeated measures ANOVA instead of an MLM. Slowly, the field, I think, is moving towards doing everything that's repeated as multi-level models, so it won't hurt you to kind of learn about them. But that's going to take a while. So lots of times, I think people are sort of afraid of them because they're kind of new, and the math on them is very, very different. If you read the chapter on this in Field's book, he basically just says, I'm not going to explain it to you because I don't understand it either. Okay, I get like this much of it. I think I understand what's going on. So we're going to talk about very traditional ANOVAs, and then I'll show you actually how to run it as AMLM as well. And then when we get to regression, we'll talk about how you interpret regression style analyses. Okay. So let's start by talking about participant numbers. So we're going to import, we have 2 different files. One of them is repeated measures 1 for one-way designs, and then we're going to get into 2-way designs if we finish. So you want to import both of those. The data we're working with right now is RM1. So I've got 4 different columns, and this is how you'll normally have the data is in wide format, like you got it in Qualtrics or something. And each participant is their own line, or traditional SPSS format. And I need to add the participant number first. So what we're going to do is use the cbind function, which we haven't used in a while, but cbind is column bind, so I'm going to take the original data and bind it together with a participant number. And so cbind the original data, so it's data set name, comma, and then what I've done, let me make this a little bigger. There we go. Is I said participant number equals, so I gave it a label. So participant number equals combine, and this looks fancy, but it's not. Let's pick it apart. So it's 1 colon, remember the colon means count in little ones, through the number of rows. So you don't have to remember how many rows there are. Okay. We've used this in-row function before for chi-square. Okay. So in rows is just going to be 8. So if I did 1 through 8 with a colon in the middle, it just counts 1, 2, 3, 4, 5, 6, 7, 8. And now that's going to get added to our repeated measures data set we have. Okay. So what do I need to change in this if I want to use it again for something else? The name of the data set. It's the only thing. Okay. So you would change this thing out for whatever the data set name is. Okay, the rest of it you can totally use. So let us run that. Do your data screening before you add the participant number. So this should go on the end of data screening. And now I just have a participant number out here on the side. You have to have that. That is new. Because otherwise, how are you going to control for who the participants are? Right? Now we can melt. So I'm going to load the reshape library. And so remember, it's data set name. Now we have an ID. So ID equals participant number. Measured equals the 4 column labels. Remember, they have to be spelled exactly right. And I just called it repeated measures 1 long. And then now I have my participant number, my costume type, or I called it costume. That's why you were asking me that question earlier. That makes a lot more sense. Okay. I called it costume in here because I, for some reason, had it in my head these were different costume types, but this is different Halloween ideas, and then our rating of how dumb the Halloween idea was. I was like, okay, so I'm going to make the column names with the caveat that it was late, and that should just be Halloween idea. So remember, the column names function just lets you rename them. So now I have a useful data set that I can do stuff with. Because variable and value are not super useful labels. So to run the actual ANOVA, let me go back to my notes here. It's ezANOVA, all in caps. Data is the first thing they go, so RM1 long, comma. Now it's dv equals dv, so everything on this side needs to stay. These are the labels you'll change. Okay, so these are all the labels that have to stay, and these are the ones I'm going to change, except 3. You only 3 alone. So dv equals dv, so our dv is the rating. WID, within subject's ID, so this is where your participant number goes. Within equals your repeated measures IVs. Between is your between subjects IVs. So next week when we do mixed design, where we have half and half, we're going to use this again. If you don't have any between subjects IVs, you just don't type it. Detailed equals true, so you get sphericity. And type equals 3, so we're doing type 3 sum squares. But since we're doing a completely different package, of course the summary is going to be different. So, and I promise I tested this multiple times last night, so hopefully the summary will work just fine. So you guys will have to install the ez library. So remember, you can click on Packages, and then Install. No, it's just easy. And then get that bad boy installed. While you guys do that, I'm going to talk about this. So you will want to include these this equals that commands, because if you decide to leave one of them out, it knows which one you're talking about. So everything we've done so far, we've just typed them in a specific order. So, you know, we did tapply, it had to be y, comma, x, comma, function. If you wanted to write them in a different order, you could, but you need to tell it which thing you're specifying. So because I've left a between subjects command out, I need to make sure I leave the little labels in here. You can actually include the labels in other functions. It really hasn't been necessary because we haven't wanted to do anything else. So the things on the left here just tell it which piece you're assigning them to. So the data is repeated measures 1 long. dv is our rating. Within subjects variables participant number, you have to have this. So that's why we had to add it. Within subjects is our different Halloween ideas that I've called costume. And then the last 2 stay the same. So you notice I left out between subjects because we don't have any. So let's run all of that. It will give you a warning. It says, I'm converting this to a factor. Okay, thanks. Okay, that warning does not hurt you. So everybody got it installed and running okay? We haven't had any weird Mac frustrations today. All right. True. All right, and then we're going to look at all this output. So just run that output again. In theory, you don't actually have to save the output at all. It's just habit at this point. So I copied it so I can make it a little bigger. And hopefully it's the same output. Like paranoid now. All right, so what do I look at this to figure out what happened in my test? Well, the first thing I want to look at is Mauchly's. Okay, so here's Mauchly's test. Remember, it's going to tell me if p is less than 0.05, but this is data screening. And we're using 001. And so this would not be significant for us. You can use 0.05 if you want, but I would say that most people think that's too restrictive. So we want it to be really, really weird. So it tells you which effect you have. So if you have multiple IVs, it'll do multiple ones, just like Levine's will sometimes give you separate ones. It calculates Mauchly's W, which is not a super useful number because you don't quite know what it is. So instead it translates that to P. So look out here at P. If it's 0, 0, 0, it's bad and you need to do something. And then the second example we have, we'll do that. If it was bad, what you do is come down here to corrections. This first one is greenhouse geyser. And so the number right under GG here is epsilon. Okay, and that's the number you want to look at. And then here's Hunfeld, and the number under here is epsilon. If the Hunfeld one is greater than 0.75, you would use Hunfeld. They're both less than 0.75, so I would use greenhouse geyser. Does that make sense, people? You're looking under the letters. And so I would use this probability. So if we corrected this, is actually non-significant, because it's pretty close. It's right on the line right now. So down here I included how would I write this up. And so I would look at just the costume line. Ignore the intercept. That's the between subjects half. So you notice you don't get total, you don't get this separate within thing. You mainly are just going to get these two numbers. And instead of putting it in a summary table, which would be nice, it writes it just a one big long line. But thankfully, the one big long line is in order. So DF in here is DF model for DF numerator. DFD is DF residual. So you just plug those in that order, so 2 and 21. Come all the way over here to F, and then there's P. All right, so you read it going straight across. Ignore the intercept line. So you'd look at Mauchly's first, decide what to do. On this one we wouldn't correct. And then you would look at the ANOVA. And this is a one-way design, so there's only one variable to deal with. You guys are way too quiet. Thoughts? Oh. All right. Well, in that case, so, yeah?
Yes. The GES, is that your eta?
Yes, we're getting there. Because I was like, I had to look it up. I was like, what the hell is this column? Because it doesn't say anywhere. I mean, yes, it is eta. Phew. Makes eta much easier. Yeah?
What if the GG and HF, what if theirs are both over 0.75?
Go with it, Hunfeld.
Okay.
So the tricky part is when Hunfeld is over 0.75, but greenhouse geyser isn't, I'd tell you to probably still go with Hunfeld. Okay. So I just kind of wrote this out. So do I need to correct? By the data screening rules that we are using, no, because P is not less than 0.001. And then we talked just now about how corrections work. If I had to correct for this one, I would pick greenhouse geyser. And if you've ever looked at this in SPSS, what it actually does is it multiplies all the degrees of freedom by the correction and then shows you partial degrees of freedom, and that's what people think you're doing something wrong because partial degrees of freedom isn't a thing. Well, it is if you correct. But since you don't see that in the output, it's not readily obvious. However, since these values are not readily obvious, not there. Bless you. Okay. You could just say that you used a greenhouse geyser corrected p-value. And I think I misspoke geyser. I think it's 2 S's. Okay. And so I tried to show you how I might do that here. Whoa. Okay. So I would list my f value, my p-value for uncorrected, and then show them the corrected p-value. Okay. So if I wanted to correct, here it is. Okay. You could also report epsilon if you wanted. But if you've ever done this in SPSS, you'll know that you might vaguely remember something about how the degrees of freedom look funny. Since that's not really clear in this output, I think just reporting a corrected P would be good. Okay. And that is probably the best middle-of-the-road solution to people who don't know how it works, so they don't realize that you should have partial degrees of freedom, so they'll be like, oh, cool, correction, and then move on with their life and not send you nasty, very long reviews. That has happened to me. All right. So, effect size. This is super nice. So, preview from John. Eta squared, the formula is still model over total, but sum of squares total is actually all of this stuff, which you don't see on the output, and that would be kind of a big pain to find. I guess you could just calculate it, but also a big pain. But fortunately, the ezANOVA function gives you eta. Woo! Yay! Okay. So I would go with 0.33, and that is where I got the one I wrote over here from. So I'm at here. It's generalized eta squared, which I think the math is just like a touch difference, but still the same idea of model over total. Yeah?
It's not partial this time?
No, because there's only one variable.
Gotcha.
It is partial on the next one. I was trying, there's a guy who wrote like a very long primer, and it's called The First Thing About Effect Sizes is You Don't Know Anything About Effect Sizes. He was trying to explain the math, but it got really late. So it's very similar to, it's like just slightly different than regular eta, but it's still that idea of model over total. And that's like nice, because at least it's on the output and I don't have to calculate. All right, here's my comments on omega squared. Oh my God, why? It's awful. So we're not. This is the formula from the book, which I don't even know, like, supposedly these two formulas are the same. This is from another book, and it's just way too much math. So we're not gonna. But you have seen it. I have showed it to you. If you talk to people about partial omega for repeated measures, people just start to laugh because it's like no one agrees on the formula. So we're just going to kind of like pretend like omega squared just isn't a thing. This is from the book I learned it from, which isn't too bad until you get to sum of squares total. And then it's just a big pain. So, we're not. Okay, so to get into postdocs, we have a significant effect. Now what happened? This is a one-way repeated measures. So we still have to deal with independence. There's only one type of post hoc because it's one way. So how do I deal with those post hocs? And so I tried to make this super clear on this set of slides. So I want to ask you that question again. Which post hoc test are you doing? We're doing dependent t. Why? Because it's repeated measures. Right. So we have to deal with it being paired. And the easiest post hoc is actually Bonferroni. Why only Bonferroni? You can do Tukey as well, but it's a bit more coding. So Bonferroni is like the fastest way to type it. Tukey will happen, you just have to code things a different way. So I'm totally down if you're like, I'm going to go with Bonferroni. I get it, it's easy to type. There is also some research that suggests that Bonferroni is less restrictive for repeated measures than Tukey, which is sort of backwards from between subjects. So the common rule is if you correct the ANOVA, go with Bonferroni. If you don't correct the ANOVA, pick your favorite. I think, no, I didn't include that. So let's run Bonferroni. I'm going to make a table. So we should be expecting how many post hocs? We got 4 groups, 4 levels. So I've got haunted house versus costume. I've got my haunted house versus punch bowl. My haunted house versus a party. And then now costume versus punch bowl. Costume versus party. And then our party and our punch bowl. Or the other way around, whatever. So we're going to do Bonferroni and Tukey. So I have 4 different levels. That makes 6 comparisons. All right, pairwise. So this is every pair compared to every other pair. Wow, I like tables, but they probably should be drawn a little straighter than this. So the way to do that, Bonferroni, is this Pairwise.T-Test. Okay, so we did T.Test before. If you stick the word pairwise in front of it, it will do all the combinations. So you do dv, comma iv, that's always y, comma x. We did y is approximately x before. Paired equals true, just like T.Test. And then we got this p adjust method equals Bonferroni. And so if you leave this p adjust method out, it's LSD, it's no correction. Okay. You got to include Bonferroni here. There are other options. It's just that Bonferroni is pretty much the most popular one out of the ones they have available. So to translate that into our data, it's DV, rating, IV, different ideas, which I label costume, varied equals true, p-adjust method, Bonferroni. This is the only reason I know it's 2 R's and not 2 N's, because otherwise it won't run. And what it gives you is different than what we've seen. Boo. So it only shows you P. It doesn't give you the means. Lame. Okay. Because this is not the other library we've been using. But it'll show me my p-values for all those comparisons. Okay. So costume versus haunt is 0.012, so that one's significant. Haunt versus punch bowls, 0.006. Haunt versus party is nothing. And then the rest of them are nothing. So essentially, there's only 2 significant ones. The haunted house is somehow different from a costume, a too small costume and a punch bowl, but we don't know how because we don't have the means. So we'd have to look at the means to figure this out. So you read this like a correlation table. It's looking at the pairs. Okay, that's fine. The other option is Tukey. So we're going to do kind of a brief MLM. So you will need the NLME package, which is like all the blendable letters in one package name. But it stands for nonlinear multi-level effects, I think. I know it's a nonlinear package, but it will do linear models as well, so it does both, so a lot of people like it. The other package, very similar to that, is LME4. I don't know what the 4 means. But I like NLME a little better. Seems to be a little easier to use than the other one. But you'll want to install that package. NLME. So we have to run this as a multi-level model. But we're not going to interpret that output, mostly because we're not really to the point where I want to explain that yet. When we do regression, we'll talk about how do I interpret this kind of output. But the way it works, remember LM is for linear models, which we do when we're data screening. So it's LME for linear models with repeated data. So you're going to do Y is approximately X. That's not new. Data equals data. It's not new. It's this thing that's new. So in the ANOVA part, oh my gosh, where is it? We did within subject's ID equals participant number. So that's how we control for the fact that participants are repeated. But once we get to doing this in a different function, it's written like this. So the only thing you're going to change here is participant number. The book has this explained a slightly different way. It does not matter if you do it my way or his way, it's the same output. So the little tilde1 is it's a random intercept. So we're dealing with the fact that some people just rate things differently. The little straight up and down arrow is to a random intercept for this variable. That has to stay. Participant number is what you're going to change. So whatever you decide to call participant number, that's what goes there. Method equals ML is the type of math that it's going to do in the background. The automatic option is restricted maximum likelihood, which tends to throw a fit and go home sometimes, for lack of a better phrase. So you want to use maximum likelihood. When we get to factor analysis, we'll talk more about max likelihood. So kind of the problem with this is like, this is a lot of things that we're going to talk about later, but here's how you run it just for this specific analysis. So what I tell you to do is to copy mine and change out the variables. So I got Y is approximately X. The only thing I changed here was my participant number. Here's the data name, and then I left it as ML. So I'm going to run that and save the output. Because if you looked at a summary of this output, actually kind of tells you what's going to happen, gives you kind of a preview. But it only shows me 3 of the effects. Right? So it actually will run pairwise comparisons, but it only shows you 3 of them for reasons we'll get to when we talk about dummy coding. But I want 6. Give me 6. So we're going to use yet another library. So 3 of them. Yeah. And it's multicomp. Okay. So multicomp is for multiple comparisons. Okay. Oh, there's no I. Sorry, multicomp. I want there to be an I so bad, but there's not.
My NM isn't running because it can't do it. I'm not getting any output.
Okay, where was that? Run. Okay, so load multicomp or multcomp. And then this function, I know it seems like a lot of work to get Tukey, but Tukey sometimes is better than Bonferroni. So the Tukey test is using glht for generalized linear something or another. Okay. And the book has actually used this package before, but we had that other cool agriculture library, so we hadn't talked about this yet. Okay. So load in the library. And so we're going to run this glht on the saved output from the MLM. That's why we had to do that step first. And then this insane looking alphabet part stays the same. Okay. So it's saying do multiple comparison procedures, that's what MCP stands for, on this IV and do Tukey. Okay. So out of all of that, I need to change my saved output. So whatever you call the output as part of the LME function. On mine I called it Tukey. And I need to change the IV name. And this will work for main effects when we get into multi-way repeated measures. So this is a way to do the main effects as well. So I called it output 2, because that's what I saved this as. And a costume is my IV. So we're on those 2 lines. And it's got cute output. I like the output on this one. It still does not give you the means. So that's why we've talked a lot about t-apply. You'll have to use t-apply to get the means. So it tells me every pairwise comparison labeled very nicely. So the hypothesis is that their pairwise comparisons are equal to 0. That's why it says equal 0 out here. And look, it's cute. It's equal. Remember, for linear, for logical tests, not 1 equals. This estimate here is the mean difference between the 2. Here's my standard error, and then it's Z. It's just Z. So anything over 1.96 will be significant. Okay. But then it's corrected. Okay, so it corrects for the number of tests. So you'll notice this 2.05 is not, because it's being corrected. So if I look at those, so I got costume to haunt here, 004. And then punch to haunt, 003. Party to haunt, 0.16. Costume to party. Did I do the next costume? No, to punch. 0.999. Party to costume, 5.6. And party to punch, 0.49. And that is why we went through so much trouble to get Tukey. See how wildly different they are. So I felt like when we did the correction talk for between subjects and ANOVAs, it was kind of like, oh look, they're kind of all the same, but look how different, especially here, they are. Okay. So the trouble of I'll go through all those extra steps for Tukey. If you have a lot of comparisons, will help with power. Because the more comparisons you have, the more restrictive Bonferroni is. Tukey is also more restrictive, but less so. So it's kind of worth the trouble to be able to get things that aren't quite so strict. And that is why we talked about it. Next thing I did down was I made a plot. You guys have seen 100 plots now, so I'm just going to show you the plot. So what happened in the study? Well, before I haven't seen the means, I've just said that these 2 are different no matter which correction I used. Haunted house and costume and haunting house and punch bowl are different somehow. And if I look at a graph, it's clear that people think the haunted house is a worse idea, because remember 12 is this was a stupid idea, than wearing something that might be cold or drinking a bunch of random booze. So the haunted house is a worse idea. Well, this is the data from the book, but I thought of poor Becca here, who doesn't like haunted anything. And then the house party is not different from any of them. So it's kind of in the middle, and it's not significantly different from any of the groups. So basically we've decided a haunted house is worse than these two, but nothing else is different. And so that's why you have to make a picture and look at the means. Because otherwise I don't know what happened, because I don't have the means as part of my output. Okay. Plus I make you make pictures all the time. All right, and that is all repeated measures one way. Yes? Okay, let me